Okay, we have one final topic for Chapter 8, and that's the topic of angular momentum. Now, the angular momentum, if you recall, when we had linear momentum was the product of mass and velocity, and angular momentum then is going to be the product of the moment of inertia, remember, which is our equivalent for the mass in a rotational frame, and the angular velocity. All right, so that's going to be L is equal to I times omega. L is a vector quantity, and omega is a vector quantity as well. We can compare this, as I said, with the expression for linear momentum, which remember we had a lowercase p for that, and it was equal to m times v. Now the SI unit for angular momentum is going to be, remember I is mr squared, so that's kilogram meters squared. And then omega is just 1 over second, so it's going to be kilogram meters squared per second, or as the SI unit for angular momentum. Now, as with linear momentum, angular momentum is conserved, and that is that Li is equal to Lf. That the initial momentum equals the final momentum. And this has a lot of different applications, just as we had with linear momentum. We'll just look at a couple different problems. If you have an object that is spinning, and then in some way its rotational inertia changes, then that will change the rate at which it spins, and that comes about here. For my initial angular momentum, I have I initial times omega initial, and then that's going to equal to I final times omega final. Let's consider a problem. Let's say that we have two spinning disks. All right, I have a spinning disk here and a spinning disk here, and they have a shaft that goes in between them. Now, initially, they're separated. All right, let's say that this object is spinning with an omega equal to 2 revolutions per second, or whatever, and it has a moment of inertia. I'll call this omega initial, and I'll call this I initial. Let's say that it has a moment of inertia of 20 kilogram meters squared. So this object is spinning. Let's say it's spinning in this direction. And then you bring another flywheel, and let's say that this has a moment of inertia equal to 10 kilogram meters squared. So these two flywheels, this one is not spinning at all. But then you bring them together, you bring these two flywheels together, they're on a shaft, and in some way they engage through gears or whatever, however you bring those two flywheels together. And then I want to know, what is the final angular velocity of the system? All right. Well, initially, all I have is this object spinning. So I know that L initial equals L final. And so my initial angular momentum is just going to be 20 kilogram meters squared times 2 revolutions per second. You could convert this, by the way, to radians per second, but we'll notice here that the units are going to cancel out anyway, so it doesn't matter. Now, L final. How do I find the final angular momentum of this system? Well, I'm bringing these two objects together. So just like we had in the toy, the clip with Richard Pryor, if I want to know the total angular momentum, I have to add up the angular momentum of this object and of this object. So the total angular momentum is going to be 20 plus 10 kilogram meters squared, and then omega final. So here I have 40 equals to 30 omega f, so 40 over 30 equals my final angular velocity, which is 4/3, or 1.3 revolutions per second. If I carry my units properly, I'll find that omega final is in revolutions per second. Because you see these units cancel over here, I'm left with revolutions per second. Notice that it goes slower when I engage this flywheel with this flywheel, and they both begin spinning, then they're going to go slower than the initial speed. This comes up a lot in rotation. see, there's a similar problem. I'll let you work that on your own. But let me talk just a little bit about a nice application. Let's say that I have a guy, and he's spinning on a disc or a wheel, like a lazy Susan type thing. Uh, so it spins freely. And he has his arms out, and he's holding two large weights. I'll show you a video of this in just a moment. He has a big moment of inertia. Big moment of inertia, and he has a certain omega. Now, let's say that he draws his arms in. So now he has those two big weights, and he's pulled them in. Now remember, I is equal to mr squared. That's the definition for the moment of inertia. So he has decreased r by a bit, kept the mass the same, but that means that he has a small moment of inertia. So, since I know that the angular momentum I omega initial is conserved, that he always has the same angular momentum, I know that if I have an I that goes down, then my angular velocity must go up. So I get a much bigger angular velocity. He spins a lot faster. I have a video you can watch. It's a demonstration. You can watch it here. It's just a moment long. Go and watch it. This comes up a lot in figure skating because in figure skating, the skaters spin a lot, and they use their bodies in order to change the rate of rotation. So I want to let you watch another clip here. It's just about a minute long, and just notice that as the figure skaters spin, how they use their bodies in order to change their moment of inertia, and thus using this idea that angular momentum is conserved, they can change their rate of rotation, omega, their angular velocity. Watch that clip here, and then that'll be the end.